So we're recording here. I'm going to share the screen. I'll do a couple of shares today. All right. Somebody else came in. If it'll share, still waiting on the share. Well, that's Anthony. Okay. Come on, man. Let's try that share again. It's not sharing. Okay. Share. You are screen sharing. No, I'm not. Having some issues with screen sharing. I had some issues in class today. Plug it in another plug. Hold on. This is great. I wish I hadn't started recording. All right, let me stop the share. I'll start again. Sorry. Not the best recording ever. Share via cable. Okay, I'll hit pause for a second while I try and figure out this, why it's not sharing. Zoom recording. So underneath the screenshots, I put links, and I'm going to beef that up. And I apologize. I need to put the link to these wrap-up videos. I missed the last couple of days. But normally the first comment is the link to the wrap-up video. And then I'm going to put links to things that embellish the discussion or things that add to the discussion. So today in class, we talked about Matt Anderson. This is Matt Anderson. And this is back from 2014. You guys can see this, I hope. This is back from 2014. And it's a 2 hour.
Talk to each other.
It's a 2 hour presentation, 2 hours and 11 minutes. So I'm not expecting you to watch all of it, and it would just start to, your eyes would glaze over after a while, because he's going into a lot of stuff, going into a lot of depth, which I like about it. He doesn't shy away from the depth. He has this glass he puts in front of him, and then he writes on the glass. It's really very effective, I think. So we looked at parts of this today.
Okay, and so this is where we're heading. The next topic, therefore, is just that, electromagnetic waves.
So he talks for 2 hours and 11 minutes about electromagnetic waves. And so if you are, look, this is what I teach is classical physics. We really aren't even supposed to spend much time on electromagnetic waves, because that's modern physics, right? We do, because it's in the, standards, but also in order to understand a little bit about how the world works, you need to understand electromagnetic waves. So we do talk about it, even though they're not really considered exactly classical. But this guy does a brilliant job of like showing you how these electrons are moving and a different energy field versus the momentum. He's talking about electron going up and down on a wire. The I means current there. He relates it to electricity. Here's the B stands for flux, or the change in. Flux is magnetic field, capital B. And so he talks about the magnetic field, and then he talks about the electric field. Then he does a really good job three-dimensionally putting them together. So when you have the electric, as we've talked about, when you have one, you have the other. And then he talks about propagation of waves. He gets into, okay, so here's how a radio works. So say an AM or an FM radio wave comes in. The electron in the wire, here's a wire, will vibrate up and down. And then that leads to a LC, what's called an LC circuit, inductor capacitance. And this is basically how your radio works. This goes off, this induces current, goes off to an amplifier. You have a capacitor there you can adjust. And so it just kind of shows how basic radio works. Then it gets into the whole spectrum. And so, like I said, I'm not wasting time. We talked about this in class. And we talked about spectrum in here a couple of days ago, so I'm not going to go into it again. But he does a masterful job. He brings in the equations, he brings in the units. So he really does teach it in a way that, and so I think if you go to about the 40-minute mark, that's probably good. It's not an assignment. It's a strong suggestion because I think you're going to come away with a much better understanding than just listen to me, give you some, all I can do is introduce ideas and throw them at you and maybe do an activity and a demo. But he's going into, and then if you want to really get into it, but I wouldn't necessarily because this is all electromag. These are electromag equations. If you just really want to get it, I mean, if you're in intensity, is cool when he talks about intensity, but he talks about how the sun, the power from the sun and all that. And so it's just pure from a layman's point of view, even it's fascinating. So this guy, his name is Matt Anderson. You should subscribe to him. This is back in 2014. There are other really good ones, Bozeman Science and of course Neil deGrasse and all those, they're really good. Brian Cox has excellent ones. So if you're out there searching about trying to get some more depth of what we're talking about and you come across something good, then you put it in the Facebook group and then I'll give you Facebook points. You're like my research points. And then if I add it, so you get, a few Facebook points just for helping me out. I've looked at a bunch of these, but then if it's something that I end up using in the comments below screenshots, then you double your Facebook points. So it goes from 3 to 6 or from whatever it is, 2 to 4, however good that is. The better it is, the more points. So yeah, keep that in mind. And the other thing we looked at, we looked at him for a while. We looked at this propagation. Yeah, this is only 19 seconds long. And we looked at this propagation of, cancel. Look at this propagation of waves. Go back. I'm not a wizard at YouTube, but so here's electromagnetic wave. There's no sound here. So the blue represents the electric wave. And I was having a hard time drawing it three-dimensional, but this kind of I like the way it's propagating. So the blue is the electrical field. The red here is a magnetic field, always at perpendicular to each other. And then the wavelength there and amplitude. So that's good to have an animation. Okay, so look for stuff like that. Now the big question, can I share my screen? If not, we're going to have a reduced class today. I do not know why it would not work. I should have turned this off and back on. Okay, share it. Moment of truth here. You might know what I'm doing wrong. I just get a black screen. That's all I'm getting. It refuses to share with the iPad.
Maybe restart the iPad.
I guess. This interruption. Let me pause it again, so at least they're not having to sit through it. We'll do something while I'm doing this, but let me pause this for a second. I want it. I'm very proud of. Anyway, so yeah, it's pretty bad. All right, so this is the. Can you see it? You can see where it says inflection point. Okay, so we'll get through it. It won't be very pretty, but so here's the the sign part, and so it says. Let me blow this up. It says to write the general equation for the ball's vertical component. Hold on. So it's A sine omega t. Hold on, let me try this. Get rid of that. Let's do that. I only have one screen to work with here, so. And blow this down a little. Okay, I know it's small. It's supposed to be small. And then I'm going to unveil it that way. So now I'm going to unveil this. Put this like that. And color that in. Fill color. All right. Now blow it back up again. Okay, so here we go. So I'm going to unveil it as we go. And so we have A sine omega t. So A is the amplitude. Now what omega though? Omega is how fast how fast the ball is going round and around and around the circle, right? How fast that boss is going round and around the circle. But that's got to translate to how fast the wave is moving, right? So omega and period are related. We talked about this a long time ago, but they're related by the function. Remember that omega is radians per second, whereas period is seconds per revolution. But we know there are 2 pi radians in a revolution. So the connection there is omega is 2 pi over TP, TP being the period. Well, the way I remember it though is that 2 pi, that TP is equal to 2 pi over omega. And omega looks like a baby's bottom. So remember baby's bottom on bottom. So it's 2 pi over the baby's bottom. So you have to, now you got to fill in specifics. But you look at this, you go, Mr. Askey, I don't know what specifics are because you didn't show a amplitude. And I think I'm going with, in class, you went with an amplitude of 2 meters. Let's see what I said here. So my amplitude is, the amplitude I'm going to go with is 4. Okay, so 4 meters was my amplitude. So I know it doesn't say that there, but we're going to go with 4 meters for my amplitude. Remember, amplitude is from the base up to either the hot maximum or the minimum, maximum or negative maximum. So 4 is I just made that up. 4 meters is my amplitude. Now, where did I get this pi over 10 though? That's the question. Where did pi over 10 come from?
Wasn't 10 your inflection point?
Well, it is. Okay, the inflection point is always going to be, let's see if this works. The inflection point is always that base point. This is I call this equilibrium. Now, what that means is, remember that, since you brought it up, we didn't talk about this in class, but let's throw it out there. The slope of this red sinusoid, and this gets into what we'll talk about towards the end after we do derivatives, but the slope of this red curve is velocity, right? Because this is position versus time. So the slope of position versus time is velocity. And so the tangent lines here, that would be flat right there, which means velocity is 0 here on the ends. But that is where the tangent line would be the steepest. And so that's where velocity is negative because in that case, you're going down, okay, on the other side here, you're going down, so it's negative velocity. But it's also going the fastest. That's the steepest slope. It's called the inflection point. And then it comes down and slows down again. But in the y direction, although you go, wait a minute, that ball's not slowing down. That ball's going at a constant rate. Yes, a constant omega, but in the y direction, it does more verticality here, if we consider this a profile view. And then it isn't going anywhere vertically here, and that's why it's 0 velocity. And then here it's going maximum verticality negative, and then here it's not going anywhere vertically. So, and that transition is by definition what a sine wave is. So, yeah, so omega is 2 pi over 20, because 20 is your overall cycle, the overall period. So 2 pi over 20 is pi over 10, or 1/10. You could say 1/10 pi there. Okay, so great. And then it's got to be students. We talked about this when some wanted to make it. Some wanted to stick in a 20 for the t, but you don't. That would make it a particular point. We're looking at a function here. Okay, so keep going. So now it says draw a project. We did that last night. That's the projection. And this is the X projection, right? And I did have some students who go, wait a minute, that's not right. You're saying X. Didn't make sense to them because you're saying X, but this looks like X is horizontal. It looks vertical to me. Yes, it's the projection time-wise of the back and forth through time. So this is still the X, believe it or not, because it's showing how the position is changing in the X direction through time. If that needs, may think about that one. But then it says to show the general equation here. Well, we see it's a cosine function, right? Cosine starts at maximum amplitude, no phase shifting here. And then it says to write the specifics. Well, this one's going to be about the same, right? It's the same. The amplitude is still 4. Now in class it was 2, so I know that's going to freak them out. But in here it's 4. And then omega is still the same. It didn't change. So your amplitude then is 4. So for the x position, 4 cosine pi over 10t. And I was being lazy here. I made them in class show the units here and show the units here. The units of omega, of course, are inverse seconds. So it makes sense because inverse seconds times seconds ends up not having units. And you don't take cosine. The cos angles, radians don't have units, right? I mean, really, a degree is not a unit either. But radians have no units. And that's what makes it really nice and convenient here, because units work out where it's the 4 meters, the units of the amplitude. Now it says to draw the omega vector. I think we may have already done that. I think we did that yesterday up here on the drawing. Sorry, it's a little bit clunky here. And on the drawing, we draw the omega there. Remember, it's right-hand rule. So if you could see me, it's going counterclockwise. So my thumb's coming out of the page. So that's positive omega. Positive omega are counterclockwise motions. Okay. Let's keep going. We'll wrap this up. Then I wanted to give you a couple of problems to work, and I'm hoping I can find those problems because those were on the. All this was on. It was nice and set up on the iPad. Okay, so now let's unveil the next one. It says. Number 6. Talks about, yes. So so the x is cosine, and the y is sine. That's not always the case. That's how I set it up this way. And so the question is, how does that sine and cosine compare? And if you look at it, they're always 90 degrees to each other. They're always perpendicular to each other. And the reason is, so they're always, and it's called a phase shift, right? There's always a pi over 2 phase shift or 90 degrees phase shift between them. And the reason for that is, sorry, I keep thinking I'm on my iPad. I can't use my fingers. So the reason for that is, let me make this smaller so you can see it. Okay, so when the boss is here, the x position is the x position's 4 meters in our case, but the y position is 0. But as the boss goes from here to up here to the top of the circle, the y position goes to 4 and the x position goes to 0. But notice that when that the sine lags, I guess, depending on your perspective, but the sine is lagging behind the cosine by 90 degrees because the cosine is measuring the horizontalness, and the verticality is 90 degrees from horizontality. So that's why the sine and the cosine always are phase shifted by 90 degrees between them. Okay, so we do that, and then we answer the rest of it. I'll blow this up, okay, so you can see that. And so we got that far in class, and then I had them go to the board. There's 6 and 7. Then I had them go to the board, and they had to write from a equation I gave them. Let's see if I can find that. From an equation, here we go. From this equation, here we go. So we don't have a board here, but you go ahead now on your paper. This is not, oh, there's a mistake here, sorry. Let me fix this mistake. I want to change this. I changed this in class. This is 12 seconds, and this is 24 seconds. 24 seconds. So from this in class, this is what the one will look like on the test on next week. And you have to write the equation from given this. So I'm going to go, Pepper's starting to cry downstairs. She wants to come up. So I'm going to go down and get Pepper. And you all, while I'm doing that, you write the equation for this. Can you see? Oh, can you see this?
We can only see the very top, where you can like have your options and stuff.
Okay, hold on. Let me, I got to share a different screen now. I think I have to share a different screen. Hold on. Golly, that really messed me up. Here we go. Now you can see this. Here it is. So now, can you see that?
Yeah.
Okay, so now that's what I want you to write. While I'm going down to get Pepper, you guys write an equation that goes with this. And then we'll write one, then we'll plot something, and then we'll be done. And we'll put a merciful end to this mess. All right. I put you in breakout rooms, but I don't trust it. Hey, baby, come on. Cry. Cry now. Cry. Belly. Okay. So hopefully you're following the format, and you can see this is going to be cosine. So I guess I'll have to type it out, I guess. So you see, so it's the A cosine omega t. Well, A is obviously 8 meters. And then we put in cosine. And then we have, I'm going to do bracket. And then my omega. Now, what's omega, though? Somebody shout out, what do you get for omega? Radians per second.
Isn't it delta theta over time?
It is delta theta over time. That's not going to work, though, very well in this one. You probably want the 2 pi over period. So 2 pi over period. The period here is 12 seconds. See, that's where the pattern repeats itself. So 2 pi over 12 is pi over 6. So we can type that in as pi divided by 6. And that's inverse seconds. Seconds to the negative first. Oh, let me get my brackets and my parentheses right. So parentheses, and let me get my superscript correct. Okay, what a pain in the tuchus. And then now you can't leave it like that because it's omega t, right? You got to put a t in there, and then the in brackets. So that would be the yeah, that has units. That's one way of doing units. The cheap man's way of doing units is just to put a bracket around the whole daggone thing and put meters out there. Like if you're in a hurry, I'll accept that, unless it says to show the units within the equation. So that would be that equation. Okay, questions on that? A girl put in 12 here today. And I said, whoops. The problem with that is you're giving me 1 point. You're giving me this point on the graph. I don't want a point. I want the function. So you got to leave that as t. Okay. And now I have another one here for you, I think. Let me back out and look. One more here if I can find it. This was me messing around this morning. Come on, man. Where was that? Oh, man. This is hot. You're going to need to look and see my workshop where I put tests together. These are the practice problems. I don't want to give you a practice. Well, okay, that'll work. No, I don't want this one. Somewhere here, I got to know. No. Oh, here it is. Okay, let's do this one. Let me zoom in on that. Let's try this one now. This one we did in class. Yeah. So let me make it so you can see it. Kill that. Hold on. Okay, let me blow it up so you can see it. So hey, so dig this. When I'm writing a test, this is test 4B stuff, but all of this is my workshop where I'm picking up problems from previous years. I can keep scanning out. I think it's like 200 pages long. There it is. And so all of that stuff turns into 2 pages for your test eventually. And that also that also includes take home. It includes the practice problems. It includes test 4A, test 4B, but doesn't help you to zoom in and look because this isn't, I haven't written it yet. Now that was stupid. Now I've lost where I thought I'd come right back to where it was. Daggone it. I almost got it. Here we go. Got her right here. Okay. Okay. Now try this, and then I'll mercifully call this good. Oh, what a mess today. I apologize. All right, so here it says plot 3 periods of the graph. They had to go to the board and do this one. Plot 3 period. I know you're sketching it out. I get it. This is, by the way, after we're done here, you should go ahead and get those practice problems out. And there's 2 problems that are just like what we just did. And while it's fresh in your mind, you should try and answer those. Anyway, this says plot 3 periods of the graph resulting from this equation. Now, don't get upset, as some did today. They said, wait a minute, Mr. Askew, why are you saying y when it's cosine? Okay, that happens sometimes. It's okay. Sometimes if it's like elevator stuff, then we're dealing with cosine. Well, actually, elevators usually sine. But things that are going like springs, and it's a vertical spring, then y sometimes could be cosine. So don't worry about it. All right, so now plot it. There's this actually came from, just to show you how far behind we are. This was packet 3. We're here halfway through packet 4. We're just getting to it, but whatever. So plot this guy. I have a hard time plotting it. So anyway, see your amplitude is 12, right? So you can do what's called, I'll put the envelope in there. You can do what's called an envelope. I can draw that at least. And so an envelope is a dashed line. Okay, I'll thicken that up. Dashed line, I'll make it dashed. Dash it. Okay, so it's a dashed line. Let me duplicate that on either side. Okay, so this shows you your boundaries. Now tomorrow, hopefully the iPad works, but tomorrow we'll look at damping those envelopes. But this is an undamped oscillator. Okay, so these are my maximums, my maximum positive, my maximum negative. It tells me it's 12, so that's my limit. Then this tells me the period, right? So that's omega. Pi over 4, if pi over 4 equals omega, remember that TP is, okay, daggone it. TP is equal to 2 pi over omega. So in this case, it would be 2 pi divided by pi. I need to show this as an equation, but pi divided by 4. So parentheses. So notice the pi's here will cancel. Pi over pi cancels. And then it's 2 divided by 1/4. Well, 1/4 goes into 2 8 times. So this is 8 seconds. So now I know another boundary condition here. I'll duplicate that and let's turn it. Another boundary condition is every 8 seconds, I repeat the pattern. So there, so it looks like at 8, at 16, getting nervous. Stupid. What the, oh, okay. Oh my gosh. Kill it. Okay, so duplicate that. At 8, at 16, duplicate again, at 24. All right, so there's my boundaries. Now here's what I can't do. I can't draw on my iPad, on my computer screen. So now you've got to fit in a cosine so that you start here, here, then you end up here again and again and again, and then and halfway between you end up here where my arrow is, here and here. So draw your cosine in 3 rounds of cosine. Okay. Now, you do that. Last thing before we go, tomorrow, I'll give you a little quick preview. Stroke color, stroke color, stroke color. Let's go blue, blue. Okay. So tomorrow, let's just kill that and go duplicate. Tomorrow, we're going to show you what happens when you damp something. So if I damp something, all of a sudden these envelopes come in like that. Now this is a linear damping envelope, which now you have to fit your cosine inside that damping envelope. That gets kind of weird, but the frequency doesn't change, just the amplitude. This is how sound waves, you know, hey, you call across the lot. Hey, well, your pitch isn't going up unless there's Doppler effect involved, but the volume drops, and that's what happens. It gets damped as it goes. So we'll talk about damping tomorrow. Shock absorbers on cars, they're all, you know, critically damped or over damped, depending what you want. So we'll get into that more tomorrow and damping functions. And then what they're doing in class tomorrow is launching the rocket. And I've got to remember to videotape it, have somebody videotape it. We never got that kid, never did give me the videotape of the hallway slinky, but I'm sorry, that's my bad. I should always be thinking about you guys, and should always be videotaping things that happen in class. We're doing a lot of demonstrations now, and I'm not really able to show you. So that's my bad. Okay. Well, because of our lack of an iPad, we're gonna have to, let me stop the share. I appreciate your all's patience. Okay, I see. Okay, don't leave. Let me take a screenshot of this, of everybody on here. Okay, so I appreciate you all's patience. And if this iPad isn't fixed tomorrow, I'll go buy a new one, I guess. I don't know. What do you do, right? Show must go on. So I will see you guys tomorrow. Stop the recording.